Okay. All right. So today we get to have our first serious example of a probabilistic machine learning algorithm for function approximation. That's why we've been working so hard last lecture on covering sort of the basic review of concepts from probability, including how to estimate parameters. So today we're going to talk about, in particular, Bayesian classifiers, and then very widely used and easy to implement, as you will soon find out, algorithm called naive Bayes classifier. It's called naive because it makes a great simplifying assumption, which is usually violated in practice. But nevertheless, it turns out to be a very valuable algorithm for a lot of practical problems, including things like, well, you can train a pretty good spam filter, even with naive Bayes classifier. So that's the goal for today. So let's jump right in. Last time we talked about the idea of having a joint probability distribution over a collection of random variables. Recall we talked about the simple case up here on the top where we might, in this case, have 3 different variables: gender, hours worked, and wealth. These are 3 Boolean variables, the way we've set it up here. And those red bars tell us the joint probability of any assignment of values to those 3 random variables. And of course, those red numbers add up to 1 because the event space is defined so that for every event, for every random draw that we do, we get some value for each of the 3 random variables. They have to take on some value. There are 3 random variables, 8 rows in the table. So of course, they have to add up to 1. So now, as we talked about last time also, if we're interested in function approximation, in general, learning to predict some variable y from a collection of other variables, say x sub 1, x sub 2, x sub 3, then one way we might try to do that is just to learn the conditional probability of y given the values for those x sub 1, x sub 2, and so forth. So here, for example, we might be interested in predicting whether somebody is wealthy or not based on their gender, male or female, and hours worked above or below 48.5. And if we did that, if we wanted to do that, then of course, because we have the joint distribution on these 3 variables, it would be possible for us to calculate that conditional distribution. So here's actually the joint distribution of, I'll call it wealth, gender, and hours worked. That's what this table is giving. For any joint assignment of those 3 variables, we see what the probability is for it. We could also instead build a table, which could calculate, of course, from the joint, for, let's say, the probability for the variable wealth given the values for gender and hours worked. And that's what, in fact, this table is. Right? So why are these numbers different? Well, it's a different table. How are they related? So somebody tell me, let's just look at this first one. So that purports to give us the probability of being rich given that the gender is female and the number of hours worked is less than 40 and a half. Then it says the probability is 0.09. How can I get that from this joint table at the top?
First, to get the rich, gender, and hours worked, that value, you put that on the numerator, and then you add that with all the things that have both the gender and the hours worked.
Exactly. So if you didn't hear that in the back, our definition of conditional probability is simply the ratio of the probability that all of these things are true, that is, you're rich and the gender is female and the hours worked, is less than 45. That would be this one. Let's call that A. So that's gender is female, hours worked less than 40, and you're rich. And then we want to know how often that happens compared to the thing we're conditioning on, which in this case would be gender is female and hours worked is less than 40. And that, of course, would be A plus B. And that'll give us this number, right? So that's just what we talked about last time. And just to remind you just how simple it is to calculate these conditional terms from the joint distribution. Okay? So if we could estimate that joint distribution, we could compile out this table, and we will have then the function we want, right? This table is the probability of y given x, and for any new person who comes in, if we ask for the values of these two attributes, we can tell them if they fall into this row, we'd say, well, your probability of being rich is 0.23. If they insist on a 1 or a 0, a yes or a rich or a poor answer, then we might say, well, since this probability is less than 0.5, if I'm forced to make a guess, I'm going to say you're poor. Okay. All right, so we could do that. But, you know, if this is what we're after, we don't necessarily need to begin with the joint distribution. We could just take our training data and estimate these parameters directly. That would be an even more, you know, reasonable thing to do. And so let's consider that. And an important question to ask is how many of these parameters are we going to have to estimate? And then will we have a reasonable amount of data to estimate them from? And if the answer to those are a reasonable number of parameters and we have plenty of data to get statistically significant estimates for them, then this is the approach we'd be happy to take. So let me just ask you then, suppose in general I'm interested in learning the probability of y given x1 up through some xn. Suppose I have n features that I'm interested in. And so I want to build a table, for example, like the one we're just talking about. Then how many parameters do I have to estimate? Well, in this table, how many parameters do I have to estimate? 4, right. There are actually, of course, 8 numbers in here. But the astute observer will notice that some of these numbers have to sum to 1, right? So, of course, the columns don't have to sum to 1, but the rows do. You know, for any given row, we're talking about a particular instance, a particular vector x. For example, the first row, we're talking about the gender is female and hours worked is less than 40. Well, either that person is rich or poor. So the probability that they're rich plus the probability that they're poor must sum to 1. So this column plus that column has to equal all 1s. And so we really don't need to estimate these. We can just estimate these 4. And then if we need the others, we just calculate them, 1 minus that. Right? Okay, so in general, if I want to estimate this for these Boolean, for n Boolean x's and 1 Boolean y, then how many parameters will I need? 2 to the n, right. Okay, and if n is 2, as it is in this little table up in the corner, then that's no big deal. If n is any kind of a substantial number, it starts to become a big deal. Right? If we have even just 30 variables, which is not, you know, not too many to ask for in a reasonable database, then 2 to the 30 is already a big number. That's like a billion. So even if we have 30 Boolean variables, we're already talking about a table that has a billion rows in it, estimating a billion parameters, calculating the other billion. Fortunately, we don't have to estimate all 2 billion. But still, a billion is a lot. And, you know, you might not want to, there are two problems with that, really. One is, it could take some computational power. But in this class, you know, we really don't care about abusing computers. It's something that computers can do at night while we sleep. So I'm not really, in this class, interested in computational arguments about, oh, I don't want my computer to work so hard, so let's not use this. I don't buy that argument. Unless it gets to be such a big deal that we can't compute it, let's say, before this course is over. Then that's a problem. If it's months of computation, that's a problem. If it's hours or even a few days for an important problem, I really don't care. But the other problem is much more unsurmountable. The other problem is, if we have a table with a billion rows, and we're going to use that formula we just talked about, A over A plus B, or directly from the data get maximum likelihood estimates for each of these for each of these parameters, each of these billion distinct parameters, then the problem is I need a lot of data. I need at least a billion data points in order to have a data point that covers each of the possible instances that I'm going to see. Right? There are 2 to the n of those possible instances. If n is 30, there are a billion possible instances. And if I'm trying to estimate this probability for every possible instance, then I need at least a billion data points. Which would be a problem if we were trying to learn to predict wealth from 30 variables in the US, because there aren't even a billion people. Okay, so that's, in that sense, it's an unsurmountable problem for us. Okay, so this is a good solution if you happen to have enough data to directly estimate these parameters reliably. Then you probably should just do it. And this is a great way to do it. However, we're interested a lot in things where we have 30 variables or 300 or 30,000 variables. We'll talk later today about a problem where we have 20,000 variables. And so then it's just not plausible to do it this way. Okay.
Sorry, just a basic question. When you talk about parameters, what do you mean exactly?
When you talk about parameters, what do you mean exactly? When I talk about parameters, I mean the values in that table that we have to estimate from the data in order to learn the function, in order to learn P of y given x. Okay? And I was using theta to represent those parameters in the previous lecture, and we'll kind of follow that convention throughout. Okay? All right. So directly estimating the parameters to get this kind of term is a good idea if you have enough data and few enough variables. But we're also interested in the case where that's not the case. And so since we know about Bayes' rule, one obvious question you might ask is, can Bayes' rule help us? And so if instead of trying to estimate here's our friend Bayes' rule, and that x could represent the vector of random variables that we were just talking about, for example, then maybe we can use Bayes' rule, because Bayes' rule says we don't necessarily have to directly estimate P of y given x. We could, if we want, instead estimate these 3 things. And in fact, the denominator can be calculated from the top 2. And so, in fact, if we just get the top, if we just estimate the top two, that would suffice. So, oh, I also put on this slide the answer to a question that somebody asked after last class. Sometimes the question was, what do we really mean when we say P of this random variable? And what do we mean when we write that kind of expression for Bayes' rule? What we really mean is that top expression is shorthand for this expression. If you recall that the uppercase letters refer to random variables, and those random variables can take on different values. And so that top expression is just the shorthand for this one, which says that for every possible value that the random variable uppercase y can take on, and for every possible value that the random variable uppercase x could take on, it's true that that particular probability is equal to that. And this is sort of more precise, but the shorthand that we and a lot of people use is just to leave out this. But every time you kind of start wondering what those things mean, just expand it out to this universally quantified statement, and it's very clear. Okay, so can we use Bayes' rule to reduce the number of parameters that we want to estimate? Well, let's ask, can we, instead of estimating this one, estimate these two? And how many parameters would be necessary in order to do that? Okay. So you tell me. Let's ask the question this way. How many parameters would it take to express that first one? Let's take this one. And again, assume we have n Boolean random variables x1 through xn. Then for this first one, how many? And how many? So let's take this first one. How many would we need for this? Now, y, of course, can take on two values, and each of these x's can take on two values. So how many parameters do we need? Yeah, let's start by thinking of y can be 0 or 1. Let's suppose, just for the case where y equals 1, how many of these do we need? 2 to the n. Right. Okay, so we need, there are 2 to the n possible ways of assigning values to x1 through xn, of course. But the probabilities associated with those 2 to the n must sum to 1. Right? Given that y equals 1, the x vector must take on some values, so they do have to sum to 1. So even though there are 2 to the n configurations, I only one of those configurations I can calculate its probability if I know all the others. Okay. So that's what I'll need for one value of y, and there are two possible values of y. Can I do the calculate thing again? Is it true that the probability for this particular instantiation of the x vector given y equals 0 is just 1 minus the probability of that given y equals 1? No, no, can't get away with it. Okay, so I have to do this for both values of y. Okay, so that's unfortunate. We're still exponential in n. If I have 30 variables, I've still got to, actually that's 2 to the n plus 1 minus 1, right? So the complexity, the number of parameters I have to estimate here is just as bad as before. Plus, I have to estimate additional parameters for this. How many? This is a giveaway question. If you didn't get that one, 1. Y is either 1 or 0, fine. Have to estimate one of those, and of course the probability that it's 0 is just 1 minus the probability that it's 1. Okay, so that didn't help. What else can we do? Well, this is where naive Bayes comes in. So I mentioned that naive Bayes is widely used because it makes a simplifying assumption. The assumption that we make in naive Bayes that changes the game, in fact, reduces the number of parameter estimates from exponential in n, that 2 to the n, to linear. And here's the assumption. What we're going to do is we're going to assume that the probability of the joint assignment of x1 through xn given y can be expressed this way. And in other words, we're saying that for each x sub I and x sub j, they are conditionally independent given y. And because of that, instead of having 2 to the n rows in a table that directly represents this, we only have to get enough parameters to represent this for all n of our different x's. Okay, so let's look at that. First, let's just kind of back up and talk about conditional independence. So conditional independence is defined here. We'll say that random variable x is conditionally independent of random variable y given random variable z if the probability distribution that governs x is independent of the value of y given z. Or put more formally, what we mean is for all the values that x, y, and z can take on, the probability that x takes on a particular value, given that y and z take on a particular value, just doesn't depend on y. In other words, what this assumption is saying is once we know z, if we're interested in the probability of x taking on any particular value, it doesn't really help us to know y also. It's not going to change the probability. Okay, and here's a simple example. I might say that thunder, rain, and lightning are random variables. At any given time, I could observe outside our window here and see whether there's thunder, whether there's rain, and whether there's lightning. And because you and I know that lightning causes thunder, and it often happens when it's raining, but lightning doesn't cause rain, and lightning causes thunder. And so we know that if we can observe accurately the value of lightning, then we know the probability of thunder. And we know that if we can also observe whether it's raining or not, that won't help us that won't change our probability of there being thunder. Okay. So there's an example of a conditional independence assumption or assertion that makes sense because of our knowledge of causality in physics. But in general, conditional independence between random variables is simply this assumption. And this is going to be something that we're going to use throughout the course. In fact, a lot of the research on how to develop effective machine learning algorithms that are based on principled probabilistic approaches, a lot of the research has to do with how to introduce different kinds of assumptions, including conditional independence assumptions, in order to make more tractable, both in terms of computation and in terms of volume of data that we need, how to make more tractable, more feasible the estimation of the parameters that we need for doing function approximation. So this is really an important concept. We're going to see it a lot. Okay, so that's conditional independence, and naive Bayes uses that we can easily derive this expression from the definition of conditional independence, and here's how. Suppose we're interested in the joint probability of say we only have two attributes, x1 and x2, given y, then first, you know, we can rewrite it this way. Why? That's just the chain rule. That we talked about that last time, right? That's just a general property of probabilities. That anytime we have the probability of some conjunction conditioned on something, we can break it down into using the chain rule in this form. Has nothing to do with assumptions. It just follows from the axioms of probability. But then to go from here to here, that's where we're making the conditional independence assumption. Because here what we're saying is, oh, this can be replaced by this. And this is where we're saying, oh, x1 is conditionally independent of x2, given that we already know y. Thunder is conditionally independent of whether it's rain, given that we already know whether there's lightning. So we can, under our conditional independence assumption about x1 and x2 being conditionally independent given y, we can simplify this term to this. And in general, that means we can take any collection of variables. If we assume they're all conditionally independent given y, then we can just express it as this product. Okay, good. So now we already asked how many parameters we'd have to estimate if we wanted these two things in the case that we weren't conditionally independent. And I think we agreed it was 2 times 2 to the n minus 1 for this guy, plus 1 more for the second guy, right? Okay, so now if we make this conditional independence assumption, notice we can now express the first of these things this way. Now, how many parameters do we need for just one of these p of xi given y's? Let's take one random variable, x sub 1. It's Boolean. How many parameters do we need to know to estimate p of x given y? Okay, I'm hearing so I think the answer, let's work it out. Suppose y equals 1, and then we'll take the case where y equals 0, because this is a conditional probability we're estimating. For y equals 1, of course, x can take on the value 0 or 1. We need one parameter for that case, right? Given that y equals 1, we'll estimate the probability that x equals 1. 1 minus that will give us the probability that x equals 0. And then we have to also consider the case where y equals 0. Same story. So we need one parameter for each of the possible values of y. Okay, so we need 2 times n. That's it. We have n x sub i's. We need 2 parameters for each of them. Plus, of course, we still need this one for p of y. But as I mentioned before, what we've done is we've reduced the number of parameters that we need to estimate from something that's exponential in the number of x features that we're using to make our prediction of y, down to something that's just linear. And now we don't care if we have 30 variables. In fact, now we don't care if we have 1,000 variables, as long as I have sufficient data to estimate them. And now I only need, well, that's a good question to think about. How much data, how many examples do you really need to estimate the n variables? You should think about that. That's a good shower thinking question. And if we had a longer lecture, we would take it up here, but we won't. Okay. So here's naive Bayes in a nutshell. You now know the whole story. We have Bayes' rule, of course, which we all embrace. We know about conditional independence assumptions, which is summarized again here. And then that leads to the following classification rule. It says, well, let's see. Let's see. Maybe it's not quite obvious why that's how we would classify the value of a new x. here's how we would assign a y. We'd find the value y that the random variable could take on. We'd consider all the little y values that it could take on. And we just want to pick the one that maximizes this product. But of course, that product is just stolen from the numerator here. So, in other words, we start with Bayes' rule, and we notice that we can rewrite, if we make the conditional independence assumption, we can rewrite this as this. And the key thing here is this part of it. And so now if we want to know, suppose y is a Boolean variable, it could take on yk, or it could take on values of 0 or 1. And now we have a new x that we want to classify. What we want to do is simply ask, well, given the values of that x, this person is male and works more than 40 hours a week. What's the probability that they're rich or poor? We could use this expression to answer it. Or if we're just interested in what's more likely, what's more probable, that they're rich or that they're poor, then we simply plug that in for yk equals rich and calculate that quantity. Plug it in again for yk equals poor, calculate the quantity, see which one is greater. In fact, the sum of those two quantities is the denominator in Bayes' rule. So if we want the probability, we just take the fraction of the probability mass out of the two cases that goes with case 1, and that gives us the probability. Okay? So it's very straightforward. It's awesome that this all follows just directly from Bayes' rule plus one little naive assumption. All right, so now we're on a roll. So here's the algorithm if you want to implement this. So what does it mean to train now? Somebody gives us a bunch of data. We want to train our naive Bayes classifier. What does that mean? Well, it just means we go through the different values of y. Let's say rich or poor for wealth is what we want to predict from those other two variables. And we just need to estimate from the data the probability that y will take on any given value. Maybe we have 1,000 people in our database and 324 of them are rich and the rest are poor. We could take a maximum likelihood estimate of p of y from that, and we're done. Then, for each value x of each attribute, each of the input variables, we also have to estimate those conditional probabilities. So for every possible value of y and every possible value of x sub I, we need to know what its probability is. And of course, some of those sum to 1, so we don't have to necessarily go through the data all the time, but we have to go through a linear number in n of those. And then, given a new thing to classify, well, we just use that expression that we just discussed, and now we have estimates. This theta and these pi's that are essentially our estimates for these and for these respectively. And given the values, the observed values for the x sub i's, we simply use the appropriate estimates, pi sub whatever, for each of the y's, and then theta for the values that are the i's and j's that are actually in the data description for that particular new x. So it's a wonderful algorithm. And of course, to do those estimates, we could just go back to our last lecture. We could do maximum likelihood estimates for each of those terms, like we just talked about doing for p of y. We could also get map estimates, maximum a posteriori estimates. And you already know how to do that. All right, so now we are going to have our first class demonstration, our first serious class demonstration. You are all training examples in a grand experiment. those of you who are sitting on this last row, on this side, you are test examples. So do not participate in training, please. Keep your hands down. The rest of you, you are all training examples. And we are going to train a naive Bayes classifier right before our very eyes to predict the important question of who lives in Squirrel Hill, the nearby town of Squirrel Hill, based on 3 other random variables, which I will call G, which is a Boolean variable. It's 1 if you shop at the Giant Eagle grocery store in Squirrel Hill. Otherwise, it's 0. And when I say you shop, I mean you have done this in the last, you've been there at least twice in the last 6 months. Then you shop at the Squirrel Hill Giant Eagle. I have another random variable called D, which is true if you drove to CMU in the last, let's say in the last month from your home. And I have another variable called M, which is true if you were a fan of Rachel Maddow. Okay. If you don't know who Rachel Maddow is, you're a 0 on that one. Okay. All right. So now, let's train our naive Bayes classifier. Of course, what we want is our naive Bayes classifier to be able to predict for future x's, the people sitting in this column, the test examples, whether or not they live in Squirrel Hill based on these probabilities that we're going to have to estimate. Okay, so first of all, let me take a rough estimate. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I've got 9 rows times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've got 90 not fully populated. Maybe, I'm going to guess I've got 80 training examples. And way too many. 6, 7, 8 test examples. Okay. Okay, so now, what are the terms exactly that we have to estimate here? Let's see, we needed that P of y, and we need the P of x sub I given y for each of the xi's, right? Okay, so let's start with P of y. That's easy. So just no participation from the test examples, please. Among you training examples, raise your hand if you live in Squirrel Hill. No test examples, please. If you we do not want to bias the training. It's not a matter of biasing the training. We don't want to bias our future estimate of the accuracy with which we train. Therefore, we need, of course, an independent set of test examples so we can see how accurate we are. Okay, so again, high in the air if you live in Squirrel Hill. I'm going to say that's 0.4 of the people. Okay, so the 0.4 of the training examples. Okay, at this point, I'm just going to cheat here. Okay, so I have 0.4 for that. So what's this one? Oh, of course we can calculate that. It's just 1 minus 0.4. That's easy. Okay, so now we want to know the probability that you drive given that you live in Squirrel Hill. So only raise your hand. Oh, I need to know how many people. I guess I already know that. Okay. I see. I'm going to need a more accurate count. I apologize for this, but for S, I really do need an accurate count. Please raise again your hand if you live in Squirrel Hill and you are a training example. Okay, 32 out of 80. I was pretty close to 0.4, wasn't I? That's pretty good. Okay, now, only if you were one of those 32 can you vote on this next question. If you're one of those 32 who live in Squirrel Hill, now raise your hand if you drive to CMU. 1, 2, 3, 4, 5, 6. Okay, so that's 6 out of how many? 32. Right? Of course, that's our definition of conditional probability. We're only interested in the subset of data for which the condition is true, and then we want to get the maximum likelihood estimate based on the fraction of Okay. Now, if you do not, do we have to estimate this, or can we calculate it from the previous one? Yeah, we still need it, right? This doesn't sum to 1 with anything we've done so far. Okay, so if you do not live in Squirrel Hill and you drive, raise your hand. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, 18 out of... Okay, we're off to the races. Okay, now if you live in Squirrel Hill, please raise your hand if you shop at the Giant Eagle in Squirrel Hill. Oh, wow, this is going to be a good indicator. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, I got 29 out. That can't be right. I got 29. Okay, if you do not live in Squirrel Hill, you're blowing my mind. You can't vote on anything we ask. Okay, if you do not live in Squirrel Hill and you were here from the beginning, then raise your hand if you shop at the Giant Eagle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. If you do live in Squirrel Hill and you are a Rachel Maddow fan, raise your hand. And if you do not live in Squirrel Hill and you are a Rachel Maddow fan, raise your hand. Okay. I believe we are done voting. Right? We need all these terms, but these other ones, we can calculate those. They're just 1 minus these others, right? Okay, so now, I don't want to take the time to, We have 8, 1, 2, 3, 4, 5, 6, 7, 8. Oh, we actually have 9 chest examples. And it's going to take us too long to do the arithmetic and all that kind of stuff. It would be too tedious. So maybe we can calculate an expression and tell each of the 9 people to, in parallel, compute their predicted answer. And then tell us the prediction and also tell us their variable values and including whether they live in Squirrel Hill. How's that? I think that'd be good. So now what do we want to do for the expression? I guess we want to say calculate. I hope some of the 9 of you have paper with you. Maybe you can just kind of the training example to your right can help you if you need help. And so what we want to know for the new people is the probability that you live in Squirrel Hill given your G, M, and D variable values is just going to be probability that this is 1 times the product, well, I'll just write out the product, the probability of Giant Eagle is your value, which I'll indicate by little g, times the probability that driving is your value, which I'll indicate by little d, given that s equals 1, times the probability that your Maddow variable, little m, given s equals 1. And then we want to calculate that, and you also want to calculate that same quantity for s equals 0, right? Okay, now fortunately, Carl is prepared to help with this. And if Carl can just tell us what these 6 numbers are, what these, oh, I see. Maybe we're there. Right? We've got the numbers here. You want to turn them into simple 1-digit things? Let's call this a 0.4. Let's call this, is this a good way to do it? 0.5? Sorry, what is that?
0.188.
0.18, okay. And this one?
3.8.
And this one?
0.91.
And this one?
0.35. 0.06.
06?
Yep. And the rest of this 0.06 as well.
Okay, good. Apparently Rachel Maddow is not a discriminating feature. Whereas it appears the most discriminating feature, well, I don't know. We'll see. Okay, so test examples. Have you finished your calculation at this point? Or just the first test example to finish may raise their hand. I feel like we should play Jeopardy music. You realize the risk I'm taking here. We only have 9 test examples. I could easily be embarrassed because if, first of all, this is a difficult prediction problem based on these 3 random variables. It could turn out that our classifier is only, let's say, 70% accurate. But because we have so few test examples, we're going to have, suppose our true accuracy of our classifier, if we were to test it on an infinite number of machine learning students, was 0.7. But if we tested only on 9 machine learning students, there could be a big variation from that expected value of 0.7 in what we're going to see here. So it's a huge risk. I just want you to know what we're doing. Okay, so test examples. Have you calculated? Okay. Okay, if nobody has one, yes?
Not exactly sure what.
Okay, your test example, your identity will be protected. What are your variable values?
Okay, so they're yes, except for S is 1, M is 0, G is 1, D is 1.
Okay, so there's test example number 1. Now, we know the true value of S, but of course our classifier wouldn't get to look at that. It only gets to look at the other 3. And so what would it predict? Let's just do it. It's going to predict, well, it's going to consider the probability that S equals 1 given this test example. And that's going to be proportional to this expression, right? So that's 0.4 times, what number do I put here? Well, G equals 1 and S equals 1, so I guess I'll put my 0.91. And what number do I put here? Well, that's drive equals 1 and S equals 1, so I'll put my 0.19 here. And 0.06. Okay, so we're interested in that and whether that's greater or less than this, the probability that, given the same test example, this person does not live in Squirrel Hill. Yes, did I make?
Last 0.06 be a 0.94 because he was false for M equals?
Oh, thank you. Yes. That should be 1 minus. Thank you. Wow. As it turns out, it wouldn't have mattered if I consistently made that error, as we're about to see. Okay, and for here, what do I put? Pardon me? 0.6. And here? Okay, let's go back. You told me for s equals 0, the probability of g being 1 was, you lied. It's 0.35. G equals 1 given. See what I mean? See what I'm doing here? His values haven't changed. It's still G equals 1, but now we're conditioning it on not living in Squirrel Hill. And that's 0.35.
You still need probability s equals 0.
Oh, I'm sorry. I see what I see. I left out the prior on y. And then 0.35. And then what's our next one? Driving given s equals 0 is 0.38. Is that right? And then being not a Maddow fan is, again, 0.94. Okay, so which of these is bigger? I'm going to cancel out the 0.94s. And I'm going to say, I don't know, without doing the arithmetic. What does the calculator say?
0.46, so the probability of s equals 0 is larger.
0.46? This is larger?
Yeah, probably s is 0 is larger.
And so the probability is that they do not live in Squirrel Hill. And how much is that probability? Do we know?
Like 0.54.
Okay, barely larger. And the answer is, oh, they live in Squirrel Hill. Okay, that's unfortunate for our classifier, but you know, in random events, errors occur. Okay, have the other test examples figured out the answers? So let's just quickly go. Give us your true value and your predicted value. Do you live in Squirrel Hill? S is 1. And the prediction is? Oh, and your variables are D is 1.
D is 0. And M is 0.
Okay. D, M, and G are... G is 1, M is 0, D is 0.
Yes.
And your prediction? We don't know it yet. Okay. Say that again? That would predict 1. Okay, excellent. Glad to hear that. Next. We're on a roll. Let's.
My ID is, mine's the same.
Okay, we'll take it.
I live in Squirrel Hill, so.
Next.
I was 1 and everything, but I predicted not in Squirrel Hill, so it got me wrong.
And you do live in Squirrel Hill. Ooh. Next. Do you know your value? All zeros. And do you live in Squirrel Hill? No. And the prediction, do we know?
It's not. It's not.
Okay, next. Okay, next. Okay. Wow, I need better variables. Yes?
0, 0, 1, and I do live in Squirrel Hill.
And the prediction was? Oh, yeah, we have that one up here. We have a lot of repeat. All right. I think we just pulled it out. So I'm going to put a check if this prediction is the same as the truth, and a minus if it isn't. Okay, so among those 8, and I've ignored this other one, which was another error. So among the 9, we got 5 correct and 4 incorrect. Okay, you can't win them all, but we won the majority. And okay, and perhaps we could have done better if we had a better set of predictor variables. But okay, now you know everything there is to know about naive Bayes for Boolean random variables that are few enough in number that we can do this in live human class time. Okay, so you see what we were doing there, and you see the importance of holding out those test examples. It was the same as when we were looking at overfitting in decision trees, that we wanted an unbiased estimate of the true accuracy of our learned naive Bayes classifier. And of course, we couldn't use U training examples to do that because we had derived the estimates from U. And so all kinds of weird stuff could happen from those estimates. For example, well, oddly, it turned out the Rachel Maddow variable was completely worthless, even in the training set. But you could easily imagine that if one more person had been on the ball about Rachel Maddow, it would have appeared in the training set to be a relevant variable. And then if we tested on the training set, it would have just looked good when it's probably not a relevant variable. All right. So there's naive Bayes. All right. So now let's look at a few subtleties that will occur if we pick other kinds of variables. Here's one of them. We can have variables that are even more rare than being a Rachel Maddow fan. So, for example, I could have had a variable which is, what is the exact date and time of your birth? It's a discrete valued variable. Well, let's say date. Let's leave out time. The exact date of your birth. That's a discrete valued variable. Since the dawn of civilization, there are a finite number of possible values. And I could have collected that. But if I try to get maximum likelihood estimates of the probability of your birthday being this one, given that you live in Squirrel Hill, I probably would have gotten a 0. Maybe I would have not got a 0, but then for some other day I would have got a 0. And then when I went to my test set, of course, they'd probably have new birthdays that weren't represented in the training set. And that would be a problem. I mean, that'd be a big problem. Why a big problem? Because remember, what we're saying is the probability of y given x is proportional to the prior on y times the product over all these x sub i's of the probability that that xi will take on whatever value we see given that y, right? And if the value we take on in the test examples is a new birthday not represented in here, then if we took our maximum likelihood estimates, that of course was what we were using there, we would get a 0. And that's a big problem. It's a big problem because it's a 0 in a product. So of course the product would now become 0. So just because you had a new birthday not represented here, we would think that it couldn't happen. Right? So we just get a total 0. So that's a problem. And so what can we do to avoid this? You all know the answer. Right, we want to use a map estimate, not an MLE. We know about map estimates. We'll put a prior on those probability terms. And we'll use that prior, which, let's say a Dirichlet prior, or beta prior. Actually, a Dirichlet prior in this case. Which corresponds to hallucinating examples. And then we'll add in the observed data on top of that. And we'll get estimates that, depending on the prior we pick, if we pick a reasonable prior, then our posterior estimate of those probability terms will never be 0, even if nobody has that birthday. Okay, so that's what we can do. And in fact, just to remind you, oops, I'm jumping around here, sorry. Just to remind you, our maximum likelihood estimates, we're just looking at, if we have some, this notation is we have some data set D. If we want to know, for example, the maximum likelihood estimate on the prior for y being 1 or 0, we just take the number of occurrences in that data set D for which this is the case, and we divide by the whole size of the data set. In other words, the fraction of cases where y equals yk. But in the map estimate, we take that same thing, except that we add in our hallucinated examples associated with each of the possible values that y can take on. So basically, we just imagine some number of cases, in this case for y equals 1 and y equals 0. Or similarly, when we're interested in the conditional probabilities, then instead of taking the fraction that we took when we did our maximum likelihood estimate, we add in some imaginary examples. So for example, for birthday, what I would do is I would add in 365 imaginary examples, one for each day of the year. Or if it was your exact birth date and year, then I'd pick, I think probably the oldest student in the class is less than 50 years old, so I'm going to take 365 times 50 examples, hallucinate those, and assume they represent one birthday in each of that 50-year period, plus leap days. Okay? So basically, by doing that, I'd be building in a uniform prior over the possible values of birthday, conditioned on Squirrel Hill equals 1, and also conditioned on Squirrel Hill equals 0. And even if none of you happen to have a particular date, my posterior estimate, my map estimate, would still be non-zero because it would have that one hallucinated example in there. And now when somebody has a new birthday not represented in the training date, I'd be safe. At least I wouldn't have a 0. It would show up as improbable, which indeed it is, but it wouldn't be a 0. Okay, so that's just the subtlety that, actually the same one that we discussed last lecture. And so I put a few extra slides in here. One thing that's worth saying explicitly, we've been talking a lot about Boolean variables, for which beta is the conjugate prior. And again, conjugate just means if we have a prior of that form, then the posterior estimate of the parameter will follow the same functional form as the prior. So if we have a beta prior and we do a coin flip binomial experiment and we get the posterior estimates of our probabilities, those estimates also follow a beta. In our case, where we're talking about birthdays, it's not a Boolean variable. Birthday is the variable, and it has 50 times 365 possible values. There's a lot of values. It's discrete valued, but it's not Boolean. And so we need a different parameter to estimate each of its, the probability for each of those values. And now, instead of using a beta prior, we use a Dirichlet prior. And to put that in more precisely, here's an example. So imagine we have a variable which is the roll of a 6-sided die. So obviously there are 6 possible values if we roll the die. Then, just like in the coin flipping case where it was a 2-sided die, a coin, in this case it's 6-sided. And so we have, if we roll that die, let's say 100 times, we'll have counts on how many times the die turns out to be a 1 versus a 2 versus a 6, etc. And if I knew that the probability of being a 1 was theta 1, and I saw that it occurred alpha 1 times, then the probability for that count would just, for these IID events, would just be theta 1 multiplied by itself alpha k times. And if I saw it turned out 2, alpha 2 times, well, if I knew theta 2, I'd multiply that. And this is just like the expression we had for coin flips, except for coin flips we only had the first 2 terms in this. And then we had a beta prior, but in this case we need a more general prior, and it looks like this, called the Dirichlet. And in fact, the beta prior is just a special case of the Dirichlet where k equals 2. It's the same notion, and when we go to get the posterior, again, it follows a Dirichlet distribution, and in practice, what that means, again, is we add in hallucinated examples, just like the birthday examples I discussed. Okay, so this is just a straightforward generalization of the beta priors to the case where instead of having 2 possible outcomes, we have 6 or 365, or it doesn't really matter. K. All right. Okay. So now there is a second subtlety. In fact, nobody complained, but you and I know that the probability that you drive to work and the probability that you shop at Giant Eagle in Squirrel Hill are really not independent, given whether or not you live in Squirrel Hill. Right? Probably if you drive to work, it's more likely that you don't live in Squirrel Hill. In fact, that's what our numbers showed, I believe. And if you don't live in Squirrel Hill, you probably are less likely to shop in that grocery store there. And so they're not independent. They're not conditionally independent either, given whether you live in Squirrel Hill. So, in fact, we could even run a statistical test, given the data that we now have, to see how likely it is that those variables are conditionally independent. But in general, they're not. And, but of course, the definition of naive Bayes is to assume these conditional independencies. That's how we got to reduce that exponential number of parameters down to a linear number of parameters in n. And so it's not really a subtlety. It's a blatantly obvious flaw of naive Bayes. I was being generous when I called it a subtlety. But despite that fact, it tends to work quite well, remarkably well, in many cases. And it's widely used. In fact, if I get some high-dimensional data set to try out machine learning classifier experiments on, often the very first thing I do is I just run a naive Bayes classifier on it, just to see if there are any signs of life in this data. So, so it is a subtlety, and it's not quite clear I can give you a proof of why it works in practice as well as it does. There is an interesting paper by Pedro Domingos and Mike Pisani from several years ago where they look explicitly at the question, why does this work so well on data sets where obviously the variables are not conditionally independent? And one of the points they make, which is a valid one, is if you test your classifier, as we did, by how many test examples it gets correct versus incorrect, then you don't really care too much about the exact probabilities it's producing. All you care is how many ones and zeros it got right. You're doing a 0-1 loss function. You're counting the, you're only looking at whether it got the probability above or below 0.5 on the right side of 0.5. And you don't even notice, if you evaluate it that way, whether it got the exact right probability. So the probabilities will surely be distorted if we make the conditional independence assumption and it's not valid. But it still could push it to the right side of 0.5. So that's one reason why. It's kind of obvious, but that's one reason why we can get away with this. In practice, if you look at the probabilities that come out of a naive Bayes classifier for high-dimensional data, that is where we have many variables, not just the 2 or 3 we were talking about here, but if I have 1,000 variables, then quite often the probabilities that come out for the predicted y are very, very close to 1 or very, very close to 0. So they tend to be distorted toward the extremes because of that independence assumption. And if you think about it, you can kind of see why. In fact, one way to think about it is, what if I have 2 copies of the same variable? Like, what if I had asked you, what if, if I had asked you the same question twice and pretended it was an additional variable? That's like the extreme example of not being conditionally independent. It's exactly the same variable, so it's obviously as dependent as it can be. Well, what's going to happen? Well, again, if we go back to our expression for how we calculate with naive Bayes the probability for y taking on any given value. Again, that's just whatever we see. And so if I have two variables that are the same, they're going to essentially get to vote twice. They're going to get to count twice in this expression. And if that variable, let's say, favors you living in Squirrel Hill, then it's going to say that twice when you multiply it out. And so obviously, we don't want that. And if we didn't make the conditional independence assumption, but instead we calculated independently every one of the 2 to the n rows in our joint table, then we wouldn't have this problem. It wouldn't matter that we had duplicate variables. The rows would just be what they were. And the only reason it's a problem is because we're assuming we can re-express this via this conditional independence assumption. So, so you really do pay a price if it's violated, and here's why. But despite that, the ease and also the fact that we could estimate, even with this many training examples, I think we probably got pretty reasonable estimates for the parameters we were estimating. The fact that it got more test examples correct than incorrect is good. The fact that it wasn't much better than random is probably more of a reflection of me picking poor variables. But, okay, so that is what it is. I think I want to stop there because I want to make sure we end on time. Question?
How do you know beforehand which variables are good and which aren't?
How do we know beforehand which variables are good to include versus not? We don't. Well, it depends on what you know about the domain. I mean, you know, you could see when I mentioned those 3 variables, I noticed some people laughed at one of the variables, so you know something about them. Nobody laughed when I said we're going to use whether or not you shop in the Giant Eagle store in Squirrel Hill. Nobody laughed. But they laughed at one of the other variables. So you have some kind of background knowledge about what might be relevant. What could you do? Let me ask back. Suppose I give you a database that has 10,000 variables, per example. Given what you know so far in this class, what kind of a test could you apply if I said to you, I want to train a naive Bayes classifier with 100 variables. Please tell me which 100 I should use out of these 10,000. What would you do? Some kind of statistical test. Anyone in particular? Yeah, good. I like it. Mutual information. That would be a dynamite way to do it. We could look at the mutual information between y and x sub I for all one of those x sub 1 through x sub 10,000s. And we could rank order the x sub i's according to how much mutual information they have with y. Right? In other words, remember definition of mutual information, it's how much they reduce the entropy in y if we condition the example on knowing the value of x sub I. So that's exactly the statistical test I would use. In fact, I would just run that, and it's a simple calculation. I just run it through those 10,000 variables. I'd rank them all by mutual information with respect to y, the thing I'm trying to predict. And then I would just draw the line after 100. Now, if it was really valuable, I'd spend a little bit more time, and I'd say, well, maybe some of these x sub i's and x sub j's are more interdependent than others. And so what I might do if I had a little bit more time is I might just ask, well, what's the single best variable? Let me rank them all and just take the top variable. But now let me calculate among the other 9,999. Let's calculate the mutual information conditioned on knowing that first one that I chose. The mutual information between the other x's and y conditioned on already having knowledge of this one, the expected mutual information. So then I would get one that was actually going to add the most, given that I'd already committed to choosing this first one. And I'd go on down that path if I was going to do it. And even that doesn't really take that long. You can see that involves a little bit more computation, but it's an easy thing to do, and it's a very good thing to do. Okay. All right, so that's it for today. See you Tuesday.
A question on that, the slide with the Dirichlet.